Pixels.
How to pack the pixel.
Yeah, pixels, resistors, and so on. Different arrangements.
And this is one single wafer.
One single wafer, 52 millimeters, 2 inches.
And you have the facility to treat these 2 inches gases.
Yeah, no problem, no problem. Only one question that our sample hold, when we do exposure, it's not 52, this is limitation.
Yes.
It's only a limitation, so it will be around maybe 45 active LA. That's all. No, we can do it in one run, very reliable, together with resistors and so on. That is good for protection against cross-polarization. When we don't protect, it's not so good, but we discuss.
Sorbet material.
Yes, sorbet material. And the same can be done for 150.
And will be only 9 or so.
Yes, it's one.
Okay.
Yes, continue, please.
So we continue with your questions.
Okay,
Another question.
always resistors.
Thermal design and thermal behavior is quite useful for this discussion, it seems to me. Как раз вот то, что надо.
Siamo lì, non le vedo un'altra abitudine uscito. No, perché è un po' difficile, ma te vuoi vedere anche piccole tutto senza polvere che danno noia, quindi il livello di segnale è quello.
Я ему уже дал. Я вчера. Ну, моя где-то гуляет. Я просто ему отдал.
Pensavo che
Как я сейчас и дам глаз. Жалко.
This example illustrates
Глаз на английском и сломать, я знаю.
irradiate
Поэтому,
whole
пожалуйста,
substrate
давай, и все будет.
on this
Его возьми, да сканируй сейчас.
ok,
active dipole, vibrator, vibrator, and the wave approach the wall boundaries of substrate.
so how
Single
is
vibrator.
time? I mean, pass in time or what?
In time,
In time, femtoseconds. Okay. Yes. Adesso è velocissimo.
Вот так.
Single.
Vibrator and the substrate 20 hundreds
Definite thickness.
Yes.
micrometers, frequency 350 megahertz.
Yes.
Да.
Ну,
это просто
разные реализации.
Too quick.
Разные реализации? Yes.
Что мы обсуждаем, что всегда предлагаем делать.
Constructions. One constructions. Number metal grid. Active elements from bolometers. Red and green X and Y active elements. The size of cells 1 by 10 millimeters.
Yes.
Как?
0.1 by 0.1.
0.1
Zero point. 0 point.
millimeters. 1 divided 10.
Ah, yeah. You can see.
Yes.
What its parameters: absorbed power and cross polarization in
5.
Yes.
And you see
for
that
this construction.
we discussed.
Bandwidth, wide bandwidth,
It's with anti-reflection coating.
with anti-reflection coating,
And very large array.
Very large array.
34 by 34. No, it's for 1 pixel.
Да, full 1 pixel.
Yes, yes.
Another construction. Another size of matrix. Wide bandwidth and
What size?
What?
size 16 by 16.
16?
Oi, 16 by 16.
No, but anyway, quite good level of polarization still. And
Dependence from
substrate.
substrate. Small dependence.
Substrate thickness?
Thickness, да, substrate thickness.
So for the thickness of the substrate,
Thickness of
one,
substrate.
one problem is the power deposited by cosmic rays. The thicker it is, the more the power, right?
Really?
Really? Yes.
Yes, I mean it goes as the volume of the substrate. I mean every cosmic ray will produce a phonon
Cosmic ray, yes. Cosmic
the,
ray, yes. Now I follow, yes.
okay, cosmic rays, protons.
Cosmic, yes.
Okay.
Protons.
Will produce phonons in the
Substrate.
substrate, and they will propagate and they
Yeah.
will excitate the SEBs. Okay,
Yes.
so thin is good. Now,
Yeah.
how
Much
thin you
better.
can do it, I don't know,
But
but
what is typical request? Because our standard substrate is around 200.
Thin, that's
90,
better.
200, 220 micrometers.
yes,
So, is it thick?
it is thick. Yes, I mean
Yes.
compared to what we did
We-
with the bolometers,
We
it's
try
thick.
to do some experiments with thickness 60 micrometers. It's
Yeah,
quite
and is a
crazy.
problem.
Yes.
But
Possible to
would it be? Can you think about working on a silicon nitride membrane or something like that?
No problem
No.
besides technological.
No, I know.
Yeah.
It's a
Yeah.
big technology problem.
No, I would like to understand scale of disaster. Because silicon nitride, of course, is good, but it's house. Micrometers, several micrometers.
Yes.
Yes. It's
10
another.
micrometers would be perfect, no
10.
problem. Yes.
We can think about it because one option that we create our substrate, our area of contact pads is thick part, but membrane just for whole structure and maybe for this 4 by 4 millimeters, it's another thickness. But 4 by 4 millimeters, it's not so small. And by the way, in this design we discussed some time ago. Let's say we need 4 by 4 area for each pixel. Can we do some rips around this? So that means it will be membrane, but in some border between each pixel we can have substrate. I suppose it's okay, yes? Simply for rigidity.
Yes, I understand.
4 by 4 it's not so good for.
It's not easy.
It's not so easy, not so
Yes.
not so easy to work with it.
So which is the idea is to put ribs
Rips, yes.
aha,
Just
in addition to the membrane. You mean.
Yes. No, between each part 4 by 4, each pixel. Not between each pixel. Between each pixel we can put the strips. And
Yes, I think sure.
Okay, we can think about it. But how serious is this influence of?
It is in the sense that the rate of cosmic rays we get at balloon altitude, okay, on in polar regions.
10 times.
Uh,
10 times what
no,
we
but
get.
I want to give you a number so that we get on silicon nitride webs.
Yeah.
Okay, we get maybe 1 per minute. Okay, and the web is 3 microns wires. Okay, and the field area is say 3% of the 4 by 4 millimeters. Okay,
Yeah.
so if you go for the full membrane, you already increase by a factor 30.
Yeah.
And if you go for the thicker membrane, you increase by
Sorry,
another.
for membrane you mean for 1 pixel or for?
Yes, we are speaking about 1 pixel.
Okay.
So in 1 pixel we have 1 event per minute.
Mm-hmm.
On a typical spider web, I don't know if you know how the spider web is made, but it fills 3 to 5% of the area.
Mm-hmm.
Okay. So you understand that if you don't have the web, you have a full membrane,
Yes.
you have a factor 20 or 30 more.
Mm-hmm.
And then this is with 3 microns of thickness. Then you add, you go with a thicker membrane and you increase by another factor.
Mm-hmm.
So you can easily get down to 1 event per second, which is a lot.
Yes. 1 event per second.
So the problem is serious. That's the only thing I can say.
Let's say will be the same or our structure is more resistive to this. Because as I understand, it will hit phonon system.
Yes.
Phonon?
Yes.
Phonon.
Phonon.
Yeah.
But phonon system.
And what say people from Planck? Probably in space this problem should be much worse, or not?
No. From
No.
Planck, it was in L2,
Mm-hmm.
and in principle should have been much better because L2 is a low radiation place. Okay, it's much better than the stratosphere.
L2, the second, yes.
Second
After
Lagrangian
Schildering.
point
Yeah.
of Sun-Earth
Yes,
system.
yeah.
Okay, so there we expected less cosmic rays.
But maybe
But we have flown Planck in a period of low solar activity, and so the galactic component of the cosmic rays was not wiped out by the solar wind.
Definitely.
And in fact, we have seen a number
And
of
most of all,
cosmic rays.
there are oscillations around L2 and rather large oscillations.
Yes, there are also large oscillations in the orbit. Yes, it's 8,000.
And this problem is
kilometers.
also obviously for them, and the reason definitely is the same, yeah? Cosmic
Yes,
rays and
cosmic
phonon
rays.
mechanism.
I think so.
Yeah.
We think so.
I was interrupted.
Yeah.
Sorry.
Yeah. Sorry.
My idea. So maybe we don't have this problem at all.
But wonderful.
Because all these bolometers, by the way, are based on full consumption of energy
Yes.
by phonon system and then
Yes.
measurement of this heating.
Yes.
All principle of our bolometer is based on decoupling between electron and phonon system.
Right.
It's basic principle.
So
if it's not, it would not
yes,
work at all.
It's insulated.
Yeah,
That's
it's
also
absolutely
also-
insulated. And difference in
Let phonon go anyway.
electron
don't-
and electron phonon interaction, several orders of magnitude. This will be decrease of this impact.
Oh yes, I mean only the events. I mean protons crossing the actual device will be, but that will be very little. I mean.
Yes, it will be very difficult to phonons to find this device.
Yes,
Because
exactly.
width is 100 nanometers.
Did you try? Did you ever see events from muons? I mean,
Might be difficult to recognize because we were doing the experiment and now in the usual lab.
yes.
Should be more careful investigation. Maybe in this case.
Because
we can-
with the kids and bolometers, we
We
do
see.
see muons even underground. I mean,
See,
we
in the
do
lab.
see.
They see?
We see
No,
muons.
no, but again, it's another principle. Kit is based on
No, I
excitement of
understand, but,
quasi-particles in large volume.
I mean,
Exactly.
Yeah.
I'm
And
trying to understand, to scale from the fact that you don't see how effective this decoupling is.
proportionally to, first of all, proportional to area, if
Yes.
it's direct
Okay.
coupling.
Yes.
It's 100 nanometers width
Yes.
and a couple
It's
of
very small.
micrometers length.
It's
And
very
that's
small.
all for direct interaction. And very thin film, by the way.
And then
10 nanometers. That's all.
I am so happy that you
Yes.
say this.
Because
Yeah.
electrodes are not sensitive.
Yes.
If you create something in electrodes, we know how to fight against any created in electrodes. I mean, quasi-particles, we put some traps there, it will be trapped more or less immediately. Only just a near area, near the bolometer, no, I mean absorber itself, could be sensitive. That
Okay.
means we can avoid this problem.
Very good.
Yeah,
Yes, very
but we
good.
find out this.
And if I can add something in the same sense, is I suspect that your detectors are very fast. I mean, very small time constant.
Yes.
So even if a cosmic ray was effectively coupled, the effect of it in the
Would be
data
very
would be
short.
much shorter. So you have to subtract many
Yes.
Less
less
data.
data.
You lose less
less
data.
data.
Yeah.
So it's
Anyway.
I
in
hope,
case,
yeah, these several
they're
factors
faster.
will help us to avoid it.
yeah.
Yes.
Yeah.
I mean, the experience with bolometers is that when you have one hit,
Oh.
it takes seconds to
Uh-huh,
recover.
yeah, of course. It's very,
So-
they are very slow. Yeah.
Actually,
about 10
we
10
use
nanoseconds.
the
10
cosmic
nanoseconds,
ray to
yes.
So,
monitor
Typical
the
scale
That's
of
also
effect of
good.
the
boson.
bolon.
okay, this means that a membrane is okay, or maybe even the full wafer is
Yeah,
okay.
maybe both ways
I
is
see.
okay. From this point of view.
Okay,
From others, maybe we can think about something.
okay,
But
so
not from this.
Since anyway, there is no need to make very thin substrates in
Exactly.
our case. No need.
Very
Okay.
Exactly, this is good.
Dependence, cross polarization from number of cells.
yes. So
You
we
see.
prefer many cells.
Yeah, it's
Many cells.
yes, it's main feature,
Yes.
and you see
Cross
it's
polarization.
natural, I would say, because when we have more and more these cells, we have better and better resolution, polarization, and basically it's only because we avoid influence of edges, some disturbance when we have larger scale.
Another
So
dependence.
it's good.
It's the same construction.
You see, we move to this level of 25, and it looks quite good.
Level cross polarization decrease.
Yes, and could you return back to previous slide? Yes, this one. Sorry, no, with this one. Yeah, you see, it's power of cross polarization. When we increase number of bolometers, this power is increased. But
This is the background, right? It's not the cross, or is the cross? And the lower curve is the background, right?
Вот на
sorry,
нижнем
what
графике.
do you mean?
This is the total power, not
No,
the
it's
polarity.
not total. This is just a question. Total power would go somewhere here. It's cross polarization power from one to another polarization.
So it's the same. It's the same with in two units,
Там
two
вот
different
рост идет.
units.
Она растет
Топ
медленнее,
граф,
чем число
lower
ячеек.
So
graph.
it's real cross polarization.
Ячейка до 900.
This is simply power, no, relative power from one direction to another direction.
Because
And
you
when we
write
increase
these,
numbers, this power looks as increased, yeah, it's really increased in absolute scale. But it should be divided by absolute power coming,
Right.
I mean this one. And this power would be somewhere here, and it's really improved. No, this is result. It's simply
Okay.
some comments.
Certo.
Okay.
Okay, continue.
Second construction, dipole array.
Okay.
Array, dipole with high resistance. This construction have beta polarization, cross polarization beta, by and absorption badly, some badly,
A little bit.
around 60% for dipole array. The array size 0.2. In the first construction 0.1. Third construction, inverse metal grid, the bolometer in down side, anti-reflection cone in upside, plane wave pull down from up side, metal. The result is average
Mhm.
from
Yes,
cross
not
polarization and
very bright.
absorption. Not bad
Yeah.
result
Mhm.
from this construction.
So, if you follow, it's two options. First option to put this array on the top of substrate, and maybe to do anti-reflection coating or not. And from the back side, it will be some metal for reflection. Second option that is described now is opposite. So we have more or less classical anti-reflection coating, substrate, and our structure from the bottom. It looks not so perfect, second option. You see 50% efficiency, cross-polarization between 20 and 25. No,
Yes.
we can do it. At least we maybe start to try this one because all our sample holders are for this option. But then we can change to that optimal option. And if we have this whole wafer, it's so easy to place on the top. No, we can do as it should be. So we'll do maybe optimal construction.
Which is the advantage of this one? Because
Advantage.
you have
It's-
already the
it's-
whole.
No,
that's
it's
the
not
advantage.
advantage, it's our traditional
Yes, no, I
arrangement.
understand.
No, we start from silicon lens, and it's classical, this Muidinus and so on. First silicon lens with anti-reflection coating, then silicon substrate from backside, our structure. It's simply repetition of the same idea. We don't change ideology. And why? Simply all our sample holders are prepared for this position, pogo pins from this side. If you do whole wafer, it does not matter because we will do bonding, of course, and so on. We can choose any. It's quite progress, it's new. It's just result of Stanislav simulations. I did not know about this option, did not think too much, but now we thought, and there is only compromise what to do, what thickness of anti-reflection coating on the top when we have the structure. Because I can repeat again, if you have lambda by 4, it's good for power matching, standard, classical. But for polarization, it's opposite. If you don't have this, it's better for polarization.
Yes.
Just here, no?
And if we don't have a polarization modulator, we really need a very.
We really,
good,
it's
very
the
good-
main parameter,
Yes, I
because efficiency can be obtained, by power, by larger scale of array.
Yes, yes.
So it's
Yes.
quite good situation now for this development.
Ну, наверное, почти все.
Да, ну, всё.
Если бы хотел, да,
Тогда может быть время.
Да, время затягивать, наверное, все.
Ага, ну все, no, we think that this part can be finished, and we can move to second part.
Maybe not finished, but now we can't say nothing about it. But lots of questions left. We should simulate all structure, maybe in the sense of received information now, and maybe finish this simulation and present in the nearest future a new result about it.
Now, what picture? Cross polarization from thickness of anti-reflection coating.
Yeah. That I try to explain by
Anti-reflection
hand value.
thickness anti-reflection coating millimeters. Lambda 4 by 4. We have
Yeah. You
minus
see,
20
from
decibels.
starting from zero thickness, we
Yes.
have minus 35, 40 dB, very good cross polarization.
Yes.
When we move to optimal lambda by 4, we have changed to 25, 20 dB.
It's a lot. Yes.
Yes.
But-
but
100% efficiency.
Yes.
yeah.
Point oh
But,
five.
but I would say only one precaution that we discussed today intensively. This point is very good, and cross polarization is ideal, but efficiency is not perfect, and some signal will be reflected. It should be good absorption around. Don't permit this signal to return back.
Yes.
Well, let's say 30-40% will be reflected and will be somewhere. That means it should be surrounded by some
Black
absorption.
body. Yes. Yes. No, that's
How-
fine.
how
That's
is-
what we
Yeah.
do.
How is efficiency for the thickness, which
Zero.
is giving a minus 30 dB,
What is efficient?
which is 0.05?
Efficiency
Да,
on
нуля.
zero,
Мощность какая принимается при...
Нет.
50%.
50%.
50, 60
No, 60
maximum.
maybe.
60%.
Yeah,
Maybe 60.
Yes, I remember for silicon it's even maybe 60, 65. Something like that.
So it looks like that an intermediate solution would be
Yeah,
the best.
exactly.
But,
And by the way, I am thinking just about this due to also another reason. First of all, this optimization, intermediate decision. And second, maybe it's good to protect our system for agent. It's
Yes.
well-known procedure named passivation
Right.
in industry. So it will be even better maybe for our. That means we can start with a relatively thin layer covering the structure and then increase and see all these properties.
So this layer is made of which material you do?
We are thinking about silicon monoxide or maybe some other materials. In principle, it's better to use material with square root of epsilon silicon. It's not perfect, but it's somewhere in this region. No, silicon monoxide, it's material that we can do. Silicon dioxide also can be done. We can choose something. So, I suppose this
Thank
is...
you for attention.
Oh, thank you very much. Will be
No,
good.
now we have
But
1 hour and 10 minutes before our next